Hello everybody, welcome to my presentation about how filtering participants improves generalization in competitions and benchmark. In competition, for example, in sport competitions, we often have at some point a selection or a qualification of the participants based on their performance. And this is mainly due to economical reasons. So you filter the participants because you can have everybody in the final phase because every participant has a cost. And we actually have the same problem in machine learning competition. So when we evaluate code submission on powerful computers like GPUs or so, we usually want to filter and to pre-select the participants to share the resources between the most promising one. And what we want to show in this work is that despite of this economical reason, there is also a statistical advantage in doing so. So this filtering can help you to select a winner that will generalize this better. To give out a bit more context, so challenges in machine learning is a growing practice, and we have hundreds and hundreds of competitions organized each year. So we have that in different platforms such as Codalab, Kaggle, or other platforms. Challenges are now part of big conferences such as ICML or NeurIPS, and they can be used to tackle a wide variety of scientific problems. So in biology, in physics, in NLP, and so on. So it's really something you can use to make science progress. And the main advantage in doing challenges in order to solve scientific problem is that the organizer, so the person who designed the problem, is separated from the participants, so the people trying to solve the problem. So in some way, it can be a benchmark that is more fair or more just for comparing the different models. So the problem we have is that we want to select a winner from a set of participants. And what we do is that we have a first phase in which we have usually a test set of data, and we compute some metrics to obtain one score for each participant, and we rank the participants using this score. So here in this example, the candidate C2 is ranked first, C3 is ranked second, and so on. However, we can't use this ranking to select the final winner of the competition because there is a huge risk of overfitting. So by making several submissions and receiving feedback on the leaderboard, participants can tune and fine-tune their methods for this specific test set. So we don't want to select the winner based on this phase. And this is why we usually have a second phase, so the final phase, where the participants submit only once on new data they have never seen. And we use these scores and this ranking to select the final winner. And so here in this example, it's finally C1 who win the competition. But the question is, do you select the more general winner? So if you had a new phase, a post-challenge phase on yet another test set, is C1 going to be winner again? And how can you select the winner that will be first in new post-challenge phase, or at least how do you select the winner that has the most probability of being better in a new phase? That's the question we try to answer, and we want to propose a method for selecting the winner. To evaluate that, we define two scores, the meta-train rank error, which is the rank of the selected winner in the final phase, and the meta-test rank error, which is the winner's rank in the post-challenge phase. And we compute also the generalization gap, which is the difference between these two scores. The method we propose is fairly simple, and as you may have guessed already, it involves filtering the participants. So what we do is that we keep only the top K candidates of the development phase, and then we select the winner in the final phase, but only between the participants we have kept. This is just this, and K is just an arbitrary parameter of the algorithm. Let's see from the previous example. So here we have these two rankings, If we take, for example, k equal 2, we select the 2 best candidates in the development phase, and then we declare the winner based on the final phase between these 2 candidates. So here it's finally C2 who wins the competitions instead of C1. Some extreme cases can be selecting k equal to n. So in this case, you just have no filter at all. You just keep everybody in the development phase, and you're back to the good old method of selecting the winner of the final phase. So here, C1. Another extreme example is taking k equal 1, and then you filter everybody except the winner of the development phase. And so you just select your winner based on the development phase, and you are prone to the overfitting as we have discussed earlier. And so the question is, which value of k will give the best probability of selecting the post-challenge winner, the general winner? In order to evaluate this, we have made experiments on real data. It was data from past competitions and benchmarks, so you have matrices of scores where each row is a participant and each column is a data set. So you have the performance of many methods of participants on different data sets or tasks. And we split the data sets randomly between 3 groups, D, F, and P. And so we average the data sets on each group to obtain one ranking. So here, D for development, F for final phase, and P for post-challenge phase. So we simulate these 3 rankings by just separating the data set randomly and re-averaging the scores. Then we can compute and select a winner using the top K method on D and F, development and final. And then we can compute the test rank error and the train rank error on F and P. So what is the rank of the selected winner in these 2 rankings? And we try this for different values of k to compare the scores depending on this parameter. So here are the results for 4 different benchmarks. On this plot, we have on the x-axis k, that is going from 1 to the number of participants, and the rank error in the y-axis, which is so the rank of the selected winner on the other rankings, but it's normalized to be between 0 and 1. So 0 would be the perfect rank, so being the rank first, and 1 means that you're last of the ranking. So the red curves here is the meta-train rank error, so it's the rank of the selected winner in the final phase, and not surprisingly, it can only decrease when we increase the number of participants we filter, because if you just select everybody, then the winner you select will be the winner of the final phase, so he will be ranked first. So that's why it can only monotonically decrease, and you have these nice train curves. A more interesting curve to look at is the blue curve, which is the meta-test rank error, so it's the rank on the post-challenge phase, so the generalization score. And here we can see that we have an optimum. So when k increases, the curve has an optimum and then goes back to its initial value. And this means that there is actually an optimal value for the filter in which the generalization improves. So that's the first main result, which is that you actually improve the generalization when filtering the participants. And we try to find a formula to select this optimal value of k star. And we can see that there is a link between the value d divided by n that you can see above the plots and the value of k. So d here is the candle distance between the 2 rankings D and F. So the candle distance is the swap distance, the number of swap you will require at least to go from one ranking to the other. And we see that we can predict more or less k star using this candle distance divided by the number of candidates n. We'll come back to this later. So just to confirm our results we obtain empirically, we also do experiments on artificial data. So here, to generate the 3 rankings D, F, and P, we first define true perfect ranking, which is so 1, 2, 3, and so on, to n. And then we do random permutations of neighbors. So we do S, which is the number of permutations of neighbors to obtain a new ranking. And we do exactly the same to obtain D, F, and P. So they are sampled equally with the same number of permutation and based on the same true ranking. So this way we can generate error rankings with two parameters, N and S. Then we can compute the score using the same technique. So we compute the top K method and then compute meta-train and meta-test rank error. And what we can see here, so we have made 4 plots on 4 experiments which are designed to match the number of participants of the real benchmarks and the value D divided by N, the candle distance. So we have chosen the number of swaps to match the candle distance. And we can see that the curves are really similar, except that they are maybe smoother because it's artificial data. So we can also see here that there is an optimal value and that D divided by N is a good predictor of this empirical value. So in conclusion, we propose this heuristic to estimate the optimal value of the parameter K, which is 1 plus D divided by N, with D being the swap distance between the two rankings, D and F. So the minimal number of swaps required to go from one ranking to the other, and N is the number of candidates. And the main result is that filtering the participants does improve the generalization. And this is true for machine learning competitions, but it's a more general result, where if you want to select a winner, that will be general in new data or new phases, then filtering the participants on the first phase will improve this generalization. And so the optimal value of K seems to depend on the correlation between the phase. So if your phases are really different, so the rankings are really disordered from one phase to the other, then you will need to filter less the participants, so to take more participants in the final phase. And if your rankings are really highly correlated, it makes sense that you don't need to keep that much participants to have an optimal generalization. So further work includes improving the mathematical framework in order to prove the results instead of just observing them in experiments. Thank you very much for your attention. Feel free to reach me if you have any question. I'll be happy to discuss that with you.